Welcome all. So we are focusing on gas laws today in live lesson. I do have a picture. I did a scorpion hunt with my son's Cub Scout group. If you guys have never done that, highly recommend. Super fun. You get a black light and go out and look for scorpions. And that's what they look like under the light. It's pretty cool. And if you're just joining us, you can do the poll at the bottom, whether you think what a hot dog is. Some announcements and other pictures. There's my dog Milo. He's a stage 5 clinger. He's usually on the floor next to me, but my son's home right now. So, Unit 2 tests, I've been grading them, and I put comments when I grade the essay questions. So if you don't like the score that you got or you want more points, you can always submit corrections, especially for the essay questions. Just send me your rewrites, and I can add those points back to your test. If you like totally bomb the multiple choice and you want to redo it, there are options for that. I do allow one reset. You would have to submit notes from the Kahoot review before that, but we can do that once for the semester. And if you didn't know, we play Kahoot before every test, and the questions in the game are the questions from the test. Welcome to all those that I just let in. Some other things that are going on around the school today at noon, we have an assembly where students who are running for a student body office are going to introduce themselves, present why you should vote for them, and then we will have voting. An email will be sent out soon after that. So come meet those who are running for student body positions, and know that you can be part of StuCo even without having a position. Okay. And they plan some events and stuff for the students. And yeah. We also have our first field trip tomorrow. We're bowling. Come out and join. We got some discounted prices from each venue since we're a school. Come have fun, meet some of your classmates, and get some bowling done. If you have PE, this could be your PE time. It would count. All right. So getting to Unit 3. Unit 3 in this class, I think, is kind of random. It's like I feel like they jumbled a bunch of stuff together to create this unit. It's not like last unit where everything kind of like went together and made sense. The first lesson talks about synthetic materials and like some pros and cons. And then obviously I added that scientific skill assignment onto it. You escaped it. Well, I mean, bowling isn't really cardio. I don't know. It can be fun. Moving your body. So we have that scientific method video. The next couple lessons, or lesson or two, talk about thermal energy and kinetic molecular theory. So all molecules move, even if they're in a solid, even like my mouse right here and your computer, it's made of atoms and compounds, and those molecules are moving. The faster they move, the more energy they have, and the higher the temperature they're going to be. So temperature measures the energy in those molecules and how fast that they're moving. Heat is related to temperature, but heat is when thermal energy transfers between different substances, like the water down here, the heat going to the water. So you have a lesson or two getting more details of that. You have a couple lessons on gas laws, and that's what we're going to talk about today. We're going to do the little portfolio assignment. It's just multiple choice. And then you have a couple lessons that look at solutes and pH, or solvents and solutes. So a solute, and hopefully this is a review, is anything that gets dissolved, and the solvent is the thing doing the dissolving. So the solvent is more the action thing. Water is usually the solvent. It is the universal solvent. Most things dissolve in water except for oils. So the other thing being added to the water would be the solute. You mix those things together, you get a solution. Now, water is H2O. When you add other things to the water, it can react with the molecule of water and change the balance of those hydrogen and hydroxide ions that make water. And that's when you can get something that has a pH. That could be an acid or a base. I guess even water has a pH. So a neutral pH it would be 7, meaning that there's equal amounts of hydrogen ions and hydroxide. So hydrogen is H plus, hydroxide is OH negative. When you add other things to the water, it could react with either the hydroxide or the hydrogen and change the concentration of each. Now, pH, specifically, we're looking at the hydrogen ion. So if it's a really small concentration, then we would be moving down or up the pH scale, get a higher pH, and you'd call it basic. If we're mixing something in there that is adding hydrogen ions or removing hydroxide, so we have more hydrogen comparatively, then we're moving down the scale. We're going to get smaller pH numbers, and those things are going to be acids. So again, those are basic things that we're covering in this unit, but today we're going to focus on the gas laws. But before we get to that, just a reminder about the different phases of matter. So gas is a phase of matter. It's the phase of matter where the molecules and atoms are furthest apart. They have the most energy. So they have more thermal or kinetic molecular energy. They're moving around a lot. You obviously can't see them, but there's gas all around your room, right? All around where you are. You breathe in gas, you breathe out gas. You go outside, there's gas there as well. Can't see it. Sometimes you can smell it. As those molecules, if they lose energy and get closer together, they can be liquid. All right. And if they lose even more energy, then they could be solid. And those are the ones, liquids and solids are the ones that we can usually see and feel and interact with more. And you're right. Matter is everything. Everything is matter that you see. It takes up space. It's made of things. Atoms are all around us. Okay, so let's watch a Professor Dave video. So this is something I learned. I called tech support to get help with the video. And I think we fixed the watching Nearpod thing, but they also showed me that I could load videos. Okay. Can you guys see the gas law video below? Okay. So we're going to watch this video together. And I've never done this. Added a video I didn't even know I could.
Hey, it's Professor Dave. Let's talk about ideal gases.
He knows a lot about the science stuff. Professor Dave explains.
Let's recall our definition of a gas as the phase of matter where atoms of a substance are in motion and fill their container. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Those are that 1, particles of a gas are dimensionless points in random motion, and the identity of the gas is irrelevant. Could be anything. And 2, that the particles don't interact apart from elastic collisions, bouncing off one another like balls on a pool table. These things aren't completely true, but they make the math easy and surprisingly accurate. So these kinds of samples are called ideal gases. When examining an ideal gas, we want to be able to discuss 4 variables. 1, pressure. This is the force the gas is exerting on its container, or rather, how much the particles are hitting the sides. 2, temperature. This is the amount of heat energy available to be transferred into kinetic energy of motion. The higher the temperature, the faster the particles move. 3, volume. How big is the container? And 4, moles. How many particles are there in the container? So, how many particles, how big is the container, how fast are the particles moving, and how often do they hit the sides? As it turns out, these variables depend on one another in interesting ways that have been formulated into laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up.
I'm going to pause this right here just so we can think about it too. And you can see that over here, it measures pressure, and we kept the molecules, the N, the same. So in chemistry, moles is a measure of molecules. It's a big number. It's like, some 6 point something raised to the 23rd, 10 to the 23rd. And it's because molecules are so small. So we need like a number that we can work with, right? Or measure. But we have the same number of particles. We decrease the volume, and those guys are still moving around, but because they're hitting the edges more often, the pressure has increased. So, and that should make sense. Like think of a balloon, or, taking a bag of potato chips up higher in elevation. When you change the pressure, you're going to change the volume. And it's going to be an opposite relationship.
This is expressed in Boyle's law. P1V1 equals P2V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant or hit the sides with the same frequency, the volume will have to expand. This means that volume and temperature are directly proportional. If one doubles, the other must double. This is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale.
And again, pausing here so you can think about it. So now the molecules are moving faster. So because they have more energy, more temperature, and that's going to change. If it doesn't change the pressure, if we keep pressure the same, then it has to change the volume. If we keep pressure or the volume the same, then pressure would have to increase. And yes, so if you, well, balloons, I mean, they can pop from a lot of things, like a pinpoint, or they drop on the grass, right? But yeah, if you keep filling it up, you'll, go past the pressure that they can handle. You're putting too much in there. Or the temperature, if you make them go so fast, it will increase the pressure. So yeah, it has to do with pressure. And yeah, like if you've taken chips from, high elevation to low elevation or reverse, like you can see a change. Like when my family comes to visit us, like if we meet in Tahoe and they live down in Sacramento area, the chips are like, they look like they're about to pop. I don't know if anyone has experienced that.
Scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius, but 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy. This helps us avoid weird mathematical issues that would arise if we were doing a calculation involving a negative or 0 temperature. To get Kelvin from Celsius, just add 273. To go the other way, subtract. The combined gas law is like a combination of Boyle's and Charles'. Avogadro's law says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Specifically, that 1 mole of ideal gas occupies 22.4 liters at standard temperature and pressure, regardless of the identity of the gas. Lastly, all the variables correlate in one equation called the ideal gas law. This also contains the gas constant R, which makes these calculations intelligible in our man-made units. There are a number of values for R depending on the units, but we will predominantly use this one. This equation is useful when we aren't looking at a change, but just to know the values of all 4 variables at once, like in this case. We could know the pressure, temperature, and volume of a gas, and quickly calculate how many moles of particles must be in the sample. So if you were looking at a sample of gas and you have 3 of the 4 variables, you can solve for the 4th using the ideal gas law. If you are given some initial conditions as well as some final conditions, you can use one of the other laws to find the other information. Just plug in what you know and solve for what you don't. Let's check comprehension.
All right, we're not going to do any equations with this. I don't think there's any on the test, but we're just going to try and make sure we understand how these laws work and relate, make sure we understand the relationships. So let's go back to the screen. Now that we have some understanding of gas laws. So the video talked about Boyle's law, which basically you're at a constant mass. So it's looking at the relationship between pressure and volume. Charles' law, which we're looking at constant pressure. So it's looking at the relationship between volume and temperature. Now, not in the video and not really a law, but it's in your lessons, is Gay-Lussac's experiments where he looked at the relationship between pressure and temperature. And that also, works with the ideal gas law. It just wasn't covered in the lesson, but in the video that we just watched. I couldn't find a good video that included his stuff too. But it will be it's in the lesson, in your course, and in the activity. So we're going to do the gas law activity together. So if you can go to your gradebook and open up Unit 3, Lesson 5, and go to the end of Lesson 5, you can fill in the answers while we do the activity. In this activity, we're using a PhET simulation, and I'm going to follow some instructions and see what happens. So Unit 3, Lesson 5. I think the best way if I split my screen. Maybe we'll just go back and forth between the tabs. I'm just trying to figure out the best way to go to do this. So Unit 3, Lesson 5. Hopefully we have the assignment open. Give me a thumbs up or some sort of reaction if you're good and ready to go. Need a little bit more time, that's fine. So Unit 3, Lesson 5. It should be, I think it's Thursday or today or tomorrow's lesson. Can't remember. Let's see, a couple thumbs up. I'll give you guys just another second to open that up. Oop. Okay. So the beginning part, we're looking at temperature and volume. And it says add light particles until we have at least 0.5 atmosphere, set the pressure to constant, and add heat to the bottom of the system. When the temperatures increase, what happens to the volume? Oops. Yeah. So let's do that. So we're going to add light particles. I'm just going to give a bunch. Our atmosphere, our pressure is more than 0.5, so we're there, right? It has our temperature right here. If we add heat down at the bottom, oh, whoops, sorry, I forgot to keep, wait, which one do we keep? Pressure constant, sorry, we need to keep, let me reset, I forgot to make pressure constant. Okay, so we keep pressure constant. So this isn't going to change. Temperature is increasing. Oops. But then volume increased too, right? Let's just do it one more time so you can see it. Keeping pressure constant, so now this shouldn't change. I'm adding heat, temperature's going up, and our volume's going up. So the first question asks, when the temperature is increased, what happens to the volume? It also increases. So click on it increases. And then the next question asks, why does this happen? So why is volume increasing when pressure is the same and we're adding heat? And the answer is that these molecules are moving faster. That heat is causing the molecules to move faster. And we have to keep, and if we're going to keep pressure constant, we have to make the volume bigger. So the heat causes the molecules to move faster. And if we're not going to increase the pressure because of the temperature, then we need to increase the space that they can move around in. So just so you can see it again, you can kind of see the speed. The speed that these molecules are moving is the pressure. And if we're going to keep that constant, we add heat, then the volume is going to get bigger, but you notice that the molecules aren't moving faster. If we didn't keep pressure constant and we added heat, the temperature would go up and these molecules are going to start moving around faster. And that's going to cause the pressure to go up. All right. So the next question, which law does this activity relate to? So in this law, we're looking at the relationship between volume and temperature. We're keeping pressure constant. And that is Charles' law. We can go back here. That's Charles' law. All right, any questions on the first three questions? Anything you want me to repeat? So the temperature, the volume's increasing, particles are moving faster and need more room to keep the pressure constant. And this is Charles' law. All right, for part two, we need to push reset, add light particles, and then set the volume to constant, and then heat the bottom. All right, so adding light particles. I'm going to keep the volume constant. So now this isn't going to change. And what do you mean no?
I kind of you know how like there's like the forward button, I kind of like use the limit's 1,000, so I kind of like tried that out a little.
Oh, on you're running it on your own. Yeah. That's good. I love that. And you can always hit reset if you're like, oh, oops. Okay, so we have we've added some particles. We've got about 6 or so ATM temperature. We're going to keep volume constant. And the question is, when temperature, what happens to pressure? When we add the temperature, what happens to pressure? Hopefully you can make a good guess. We'll see if your guess is correct. We're adding heat. And you can see, we're going to blow up the thermometer. But the pressure was increasing. If we're keeping the volume constant, those molecules are moving faster, and we're keeping that space the same, then that pressure is going to go up. They're going to be hitting the side more often, which we can obviously see. Okay, the next question says, add more particles using the double arrow. What happens to pressure? Whoa, now it's getting crazy. It still increases. So next question, why? Why is pressure increasing for that? Why is pressure increasing? Because we have more particles, which means more collisions. So that's more pressure. So the more collisions, basically the pressure is the collisions. The more collisions there are between those molecules, the more pressure. So making them move faster, adding more of them, both of those can increase the pressure. Question 7 asks, what happens to the pressure when particles are removed? So we can open the top here and we can release some of those particles. And we can see that pressure is decreasing. So for 7, it decreases. And for 8, why? It's kind of the opposite of the other question. Fewer particles mean fewer collisions, which is less pressure. Questions here? And this activity relates to, we're looking at pressure and temperature. And that's Gay-Lussac. His was the one that looked at pressure and temperature. All right. Any questions on the questions in part 2? Ready to move to part 3. Temperature is a constant. All right, so reset the simulation, add 100 heavy particles, set temperature to constant, change the volume by sliding the box in and out. All right, so I'm going to reset. I'm going to add 100 heavy. Give it a second to figure itself out. These heavy ones move slower for sure. And now we're keeping temperature constant. We can't change the temperature. And then we're going to change the volume. So this isn't going to change, but we have pressure. Let's see what happens to the pressure when we make the volume bigger. You can see pressure went down. If we make it smaller, pressure goes up. Okay. So in the question 10, when volume is decreased, what happens to pressure? So if we decrease our volume, we've increased pressure. Okay. The opposite, if we make the volume bigger, then we decrease our pressure. So why is it increasing? This is question 11. Why is it increasing when we decrease the volume? Because we have less space and those particles are going to hit the side more. So again, pressure is all about how often the molecules hit the side. If we make this big, they have more space to move around. They're not going to hit the side as often, so pressure is less. When it's small, less space means the particles hit the wall more often. And then the last question, which law does this activity relate to? It is Boyle's law. So, Boyle's law, PV equals P2V2. That was Boyle's law. And then those are all the questions for the activity. It was just so you can play around and kind of see on your own what happens when you manipulate those particles. And just as a reminder, Avogadro's law It's looking at, like, if you have a constant volume, then you have the same number of molecules no matter what the molecule type is, whether it's, carbon dioxide, oxygen, nitrogen, whatever. And a mole, what N is, N represents a mole, not the cute little animal, but a mole in chemistry is an amount. It's like saying I've got a dozen of something. You can have a mole of something. It's just a lot of it. 6.02 times 10 to the 23rd. So that's like, I don't know it's more than a trillion. I don't know what that is. It's a mole. That's his number. And again, we're talking big numbers because these are little teeny tiny things. So again, a mole of hydrogen is the same number of atoms as a mole of water. You have that many water molecules. 6.02 times 10 to the 23rd. And then the ideal gas law combines all the different laws and the relationships together. So pressure and volume equals number of moles times a gas constant times temperature. All right, any questions? Any questions on the little activity or any of the gas laws? That works. And one nice thing about this is, you've seen a lot of this in your daily lives with balloons and, bags of stuff. All right, let's go to our poll, see who's winning or what the biggest thought is. Yeah, kind of a tie between a hot dog being a taco and neither. Well, we're only one off. Sandwich has 3 votes. Now everything's even for those who have voted. We'll never know. Is a hot dog, is it a sandwich, a taco, its own thing? Why? I think it's more of a taco. That bread is connected, right? You think it's a hot dog.